Okay, so we're going to look more into the functions themselves, and we're going to determine the zeros of a function. So for instance, if I give you y equals x plus 1, this is very basic. If I want to find the zeros, then what I can do, I can make a little t-table. Here's your x value, here's your y value. I can set x equal to 0, I can set y equal to 0, and I can solve. So if I set x equal to 0, I have y is equal to 0 plus 1, which means y is equal to 1. So this 0 would be the ordered pair 0, 1. And if I put y is equal to 0, then I have 0 is equal to x plus 1. Then I subtract the 1 and I get negative 1, 0. And so I get a line that looks something like the following. There's a point here. There's a point here. And I draw my line. And you're probably wondering how I know this is a line. You might not. If you do, then all that I'm looking at is the fact that that is just x to the power 1. So that is why that is a line. So finding the zeros of lines is very straightforward. You guys have found zeros of quadratics, and so we're going to actually, oops, I didn't mean to do that. We are going to actually do that right now. So if I give you the equation, let's use something familiar, or close to familiar. If I give you y is equal to x squared minus 1, then x's, so let's do zeros. If I plug 0 for x, then I have y is equal to 0 squared minus 1, which means y is equal to negative 1. So 0, negative 1 is one of my zeros. Okay, so if I plug 0 for y, I have 0 is equal to x squared minus 1. So I solve it, I add the 1. I have 1 is equal to x squared. I take the square root and I get x is equal to plus or minus 1. So what does that mean? That means my zeros are 1, 0 and negative 1, 0. So I get two separate ones. Remember, y was 0 in both cases. So that is taken care of. Pretty straightforward on finding zeros of quadratics. If you're going to do cubics and quartics, it can be, the cubics just means y is equal to x to the third and the likes of that. Quartics is just y is equal to x to the fourth. And you'd plug in zeros for x and solve it, and you'd plug in 0 for y, and then you'd have to try to factor it. So it can be done. So with that being said, sorry, my alarm's going off. Make sure I'm out of bed and ready for our meeting today. But we have rational functions. If you want to find the zeros of rational functions, it's not always possible, but it could be. If I give you y is equal to 1 over x, for instance, and I ask you what the 0 is, so if I say x is equal to 0, then I have, this implies y is equal to 1 divided by 0. And it's at that moment where you should say, wait a second, that's not legal. This is undefined. Okay, so this is undefined, and therefore there is no, what do we call this? No x-intercept. Okay, so that's taken care of. And then if I give you y equals 0, then I have 0 is equal to 1 over x. Well, 1 divided by how many parts is going to give me 0? Well, it should be pretty obvious that that number would have to be insanely big. But unfortunately, if you take one of something and you just divide it into pieces, you're always going to have some amount of pieces left, no matter how small those pieces are. Remember, if I do 1 divided by a million, then I still have something. I have a very small something, but I still have something bigger than 0, even though it's very close to 0. If I do 1 divided by, I don't know, 100 billion maybe. That's 100 million, so let's add some more zeros. That's 100 million. Yeah, that's a billion. 100 billion. I still technically have something. It's probably like 0.0000. I don't know how many zeros it's going to have, but 1 or something like that. Actually, it'll probably have as many as this has. But the goal here, what I want you to see is that I always end up with this 1 here, which is bigger than 0 technically. And so this is undefined as well. And you're probably saying, but I thought you said we were finding the zeros of a rational function, and it can be done. Well, it can be. The graph of this one looks something like the following. Let me think. It's so it doesn't cross the x or the y axis. And if we put negative values, it's in the negatives. If we put positive values, it's in the positives. And so that would be our graph of this thing. Now, when would it have an x-intercept? Well, if I put y equals 1 over x, not an x-intercept, a y-intercept, plus 1, for instance. Actually, it could still have an x-intercept, I believe. I'm sure it could. Actually, this will. No. Yes, this will have. I think I said that backwards earlier. When you set x equal to 0, this is the y-end. I'm sorry. This is the y-intercept. Sorry, you get the opposite. I don't know what I was thinking a minute ago. So I gotta fix that. Okay, so this would give us the x-int. This one's the y. Then when you set x equal to 0, you get the y-intercept. Sorry about that. When you set y equal to 0, you get the x-intercept. I apologize. I should have said that right the first time. But here we go. We're going to set x equal to 0. Well, you can't do it. It's still undefined. Why? Because you get 1 over 0. But if I put y equals 0, then I have 0 is equal to 1 over x plus 1. Then I subtract 1. I have negative 1 is equal to 1 over x, and then I multiply both sides by x, and I have negative x is equal to 1, and then I divide by negative 1. And now I have x is equal to negative 1. And so if I have negative 1, 0, I have a point on this graph. So this graph looks something like this. It goes to negative 1, 0. And it sort of goes like this. Oops, that's ugly. I don't like that. It shouldn't be square. And then we start getting into things like asymptotes, which is not part of this lesson today. I don't believe it's coming up, but not today, maybe next week or the next video set. But with that being said, that is your rational function and the zeros. Now, if I ask you the domain and range, that's where it starts to get more and more tricky. If it's a line, the domain and range is just all real numbers. It's negative infinity to infinity. If I ask you a quadratic, the domain is negative infinity to infinity, but the range is limited based on what the lowest value of y or the highest value of y is. And now we're going to look at the rational function. And so let's look at this one. And so what I'm going to do is I'm going to say domain and range. If I ask you the domain of this, then what you're going to tell me is any values where x can be a real number. And so the first thing you ask yourself is, can I divide by 0 in this problem? And the answer is yes. And the reason it's yes is because this has an x down here in the bottom. When do you divide by 0 in this problem? The answer is when x is equal to 0 itself. For instance, you could have maybe 1 over x plus 1, and if you have that one, can you still divide by 0? The answer is still yes. But now it's when x is equal to -1 instead. Okay, so you have to be very careful. So x is equal to 0 is where this is equal to 0, so x cannot be equal to 0. So to write this, what we're going to do is we're going to go from -infinity. Pretend you're on a number line. Here's 0. We have -infinity over here. And then we have 0. And then we're going to leave 0 out. Exclude it. That's why this is open. And we're going to jump over it. And we're going to go to the other side of 0. And we're going to go up to +infinity. Those are all of the x values we can use. It's interval notation. And then the range of this, that one's a little bit more tricky. You have to know the asymptotes to do that. And so this one's asymptote is at 0. This one moves it up 1. And so our asymptote's at y equals 1. And therefore that means that there will be no points going through that. It will approach 1 for the y values, but it will not get to 1, just like in this one down here. It approached 0. Remember, we said it doesn't touch 0. In this case, we could not find a solution down here. And so the range of this is going to be -infinity to 1. And then 1 to infinity. And what that means is the lowest values down here are -infinity. Sorry, we're looking at this. It comes up. It gets to this 1 right here. It doesn't have any values at that 1, but it has values right above it and right below it. And then it jumps over it over here, and it comes up to +infinity, which is up here. Okay, so left to right when you're looking at domain, top to bottom when you're looking at range. And so that is an example of a rational function. If we look at radical functions, maybe I give you the square y is equal to the square root of x plus 7. If you wanted to know the domain of this, then you need to find out where the square root is equal to 0. So we have the square root of x plus 7 is equal to 0. Well, that means we square both sides. We subtract 7, and x is equal to -7. Now, we have to ask ourselves, is it the numbers to the left of -7 that are giving us negatives, or is it the numbers on the right? So if I plug -8 into this, if I put -8 plus 7, that's -1. The square root of -1, that's not good. So -8 does not work. So we're actually going to start at -7 and go to the right. So the domain will be from -7 to infinity. Now the range of this, I know the graph of this looks something like the following. Here's -7. And it curves and goes upward. You will get more and more familiar with this the more you practice it. And so the lowest value here is what this point here is, which is -7, 0. So 0 is in the range. And it goes up all the way to +infinity. This is technically going up no matter how slow it is, but it will, I mean, you could always give me a bigger and bigger number to get closer and closer to infinity. So, all right, I'm going to end this video here. We'll talk about the other ones in the next video. I hope this isn't too much information. I know this is a lot. It will take practice. Make sure you're doing ALEKS for these. Thank you.